Today we're going to focus on physics grade 12. Topic is work, energy and power. Work, energy and power. So we are going to be helping each other on how to calculate such kind of problems, and then in a simplified manner, so that you can understand them better and calculate very clear and simple. So under work, energy and power, we are going to use grade 11 concept, and then that grade 11 concept that we're going to be using is Newton's principles, and then we are going to find work done by those forces that we use to calculate in grade 11. So I'm assuming that you understand the concept of object on the horizontal surface. You understand the concept of objects on an incline. So you understand how the force applied on the object is either they are applied parallel to the surface, or forces are applied at an incline or at an angle, or maybe we can talk about the object that the force has been applied from the backside. Maybe it's been pushed or it's been pulled. So, and then it's going back to defining what is a force. A force is a pull or a what? Or a push. So now this is the concept. So every single time when you calculate such kind of questions, we focus on the work done by the force, either in applied, either tension, either friction, either weight, either normal, and either parallel. So depending on where is our object and then how the force is applied to. But now the main focus is the force now depends on the path taken. So it's either the force is going to the left or to the right, or in the direction of the object, or in an opposite direction with the object. But the main focus is we talk about where now the distance that that object is going to cover. So in work we have the first one where we have work net equal to F net delta x cos of theta, where we say that work net is the sum of work done by the forces that are present on the object, that are doing the work. And then with the distance that that particular object is going to be covering, and then the theta represent angle, cos theta represent the direction in which the force is going with. So if the force is going in the positive direction, then the cos is 0. If the object is going in a negative direction, then the cos is negative, or the cos is 180. So this one is the sum of the forces of all forces, and then this one is the displacement. This one is the displacement covered by the object or the force, and this one is the direction. This one is the direction. So now, as this one is the sum of all forces, you remember that Newton's second law, we say that the sum of all forces acting on an object equal to the mass multiplied by the acceleration. Right, so now the interpretation here is the same story, and then here is the distance that that particular object or the force is going to be covering, and then this is the direction in which, where is that force going? Is it going the same direction with the object or not? If it is, it's cos 0. If it's not, it's cos 180. So we have another one where we have work net equal to change in EK. So work net or change in EK, these are the same. The difference is this. Here we talk about the forces acting. Here we talk about the mobility of the object, the kinetic energy, movement from one point to another, the velocities, how it moves, how fast it goes. So now we talk about the movement from one point to another, relating them to the velocities in which you're going. So this is what we call work, energy theorem. This is work energy theorem. When they ask or they say state work energy theorem, what do they say? You say it is the net work equal to the change in kinetic energy. Note that in the concepts or in the test or the examinations, every single time when they ask you a question that define Newton's second law, note or be informed that the second question that is coming is for you to calculate that particular principle. If they ask state Newton work energy theorem, note the second question will be using energy principles or using work energy theorem to calculate. Always note. But immediately you see work energy theorem, note that we are going to be using kinetic energy, movement of the object. Now, so in terms of the work net is equivalent to work done by applied plus work done by friction plus work done by normal plus work done by gravity. The sum of all these things equal to or sum up to work net. The sum of work done by respective force, applied, friction, normal, gravity. So this is the sum of everything. So for the likes of maybe a question comes to say calculate work done by friction. If you have applied, you can substitute this. Here you use the F net and then you calculate. But that one will deal with them when we talk about or when we do examples and see how we can calculate those problems. Now, work done by applied is where FA delta x with the cos of the theta. Work done by friction is FF distance cos of the theta. Work done by gravity is FG distance cos of the theta. Work done by normal is Fn distance cos of the theta. Remember that the sum of all these things, they sum up to work net, right? Depending on how many forces you have. So this formula is not different from this one. The only difference is this one is when you talk about the sum of all forces. Here we're not talking about the sum. We talk about the work done by that respective force that applied, that is there. And then the distance is covering and then the direction is going to take. Is this force going in the same direction with the object or not? If this force is going to the right and then the object is going to the right, this is cos 0 degrees. Now, if friction, or remember, friction is always opposing the motion. Therefore, this is cos 180. Cos 0 is positive 1 and then cos 180 is negative 1. This is the direction in which I identified from this cos. This cos tells us the direction. But when we substitute here, we substitute the magnitudes of this. We don't substitute the signs of these forces. We substitute the magnitude of these forces. But the sign of the direction is determined by the cos. Is it going the same direction with the object? Yes. Then it's cos 0. Is it going the opposite direction with the object? Yes. It's cos 180. So let's demonstrate this in simple terms of maybe Cartesian plane, just to understand this concept. But before I go to Cartesian plane, let me also talk about this one. Work done by weight. Work done by weight is always like this. But remember that weight, how is it operating or how is it working on the object? Weight and normal, they are working perpendicular to the surface. And then as long as they are working perpendicular to the surface, perpendicular means they create an angle of 90 degrees. Meaning that this angle is this 90. So for normal, the angle it creates is 90 degrees. Therefore, work done by normal is always 0 joules. It's always 0 joules, right? And then work done by weight is always also 0 joules. Work done by gravity is going down. It's cos 270. It's because the angle it creates is 270. And then work done by normal is 90 because it creates a perpendicular angle. So on the Cartesian plane, if we were to use it in that fashion, then we can use it. Let's draw it here. We can use the Cartesian plane here, right? And then we say that looking at this, 0, 90, 180, 270, and 360 degrees. So looking at this, if the object is moving along this way, it's 0. That's why we say it's cos 0, right? So let's show it by, I believe here you don't see very well. Let me just show you with a big Cartesian plane, or maybe a free body diagram of some sort, so that you can see it. So we can check that here we have 0, here we have 90, here we have 180, here we have 270, here we have 360. So if the object is moving along this way, it's cos of 0. But it's cos of 0 only when the object is moving in the same direction with the object, right? And then another part is that here, the angle here is 90 degrees. The angle here is 180 degrees. The angle here is 270 degrees. So now, for the likes of applied force, it's cos of 0 because most of the applied forces are going the same direction with the object, right? And then friction is always 180 because friction is always opposing the motion. If the object is going this direction, friction is going this direction. That's why it's cos of 108. But now, the reason why we are saying that work done by weight is 0 is because now we need to check how is that force related to the surface of the object. Is it in line with the surface of the object or perpendicular, right? We substitute the angles that we have. For the likes of weight, let's start by saying, this we said is the direction. Where is our weight going? Our weight is going downwards. So as it's going downwards, what is the angle it creates? It creates an angle of 270. So if I were to substitute 270 here, you see that here I substituted 0, here I substituted 180, which means here I substitute 270. If I substitute 270, cos 270 is 0. So because I'm multiplying everything here is 0. Therefore, work done by weight is not doing any work on the object. Another one, normal. Normal also works the same way. It's acting perpendicular. Therefore, I put 90 degrees here, then everything becomes 0. Then it tells us that work done by weight and work done by normal, they are not doing any work on the object because the force is acting perpendicular to the direction of the object. That's how we calculate work problems. So we look at those problems and then that's the interpretation of them. So now we are moving along to energy and then see how it works.